Hi everyone, Queeveen here from the comfort of my kitchen. In today's video, we are going to be at least discussing the shape of various objects in the sky. Hopefully we'll be able to see the shapes of these objects in the sky and you'll be able to see what I'm talking about. But we will at least be discussing them. We're going to take a little bit of a break from the eclipses, although I will make another video in the near future talking about the very long eclipse that's coming up in the far future in the 2100s. So we will be looking far into the future for that in a near future video. Hopefully I will be posting that soon. Also, there should be a video this week. It may already be up, it may be coming up in the next couple of days. There is going to be a video on my third YouTube channel, Queeveen's Content Osgoelga, that is linked in the description, just in case you'd like to take a look at it. It will have subtitles in English. But we're here, first off, to make a quick comparison between Venus and Jupiter. These are planets, and one of the defining characteristics of a planet is its shape. Dwarf planets and planets are the objects that can become round or reach hydrostatic equilibrium. The planets aren't quite as close as I'd like them to be, but we may still be able to make this comparison. If we take a look at Venus here, an incredibly slowly rotating planet, it looks pretty round. And it is pretty much a perfect sphere. It rotates incredibly slowly, so its gravity is able to pull it into a sphere without too many forces combating it or pulling it in different directions. Jupiter, on the other hand, is very much an oblate spheroid, and technically the Earth is an oblate spheroid as well. However, Jupiter, and I think we can see it here, Jupiter is definitely wider around the middle than it is from pole to pole. Jupiter, of course, rotates incredibly quickly. Its whole day is just, almost 10 hours. We're seeing it here as 9 hours and 55 minutes. Because of Jupiter's incredibly quick rotation, it's bulging around the equator. The centrifugal force, centrifugal force, centripetal force, there are various forces and pseudo-forces, but we won't get into the discussion of that nitty-gritty part of physics in this. All I will say is that due to the very quick rotation of Jupiter, it bulges around the equator. Material around its equator is essentially being spun away from it. Its gravity is still able to catch it and keep it in shape, but it does bulge around the equator compared to its distance from North Pole to South Pole. So we can see that here. I hope you can tell that Jupiter is a little bit wider around the middle. And if we hop back and take a look at Venus again, we're going to see that Venus is just that little bit closer to a perfect sphere. And you can, I hope you can see that. I certainly think it's visible here. Even without all of Venus visible, we can see that it is a lot more even. It doesn't quite stick out around the equator as much. That's down almost entirely to the speed of its rotation. Now, of course, Venus is a rocky planet. Jupiter is a gas giant, and gas is a little bit more malleable than a solid. But Venus, it does have a very thick atmosphere. So if Venus was rotating very quickly, we'd at least expect its atmosphere to bulge, even if its physical material doesn't. The Earth also bulges a little bit around the equator, which is why, even though Mount Everest is the tallest when measured from ground level, it is the tallest mountain, there are mountains around the equator like Mount Chimborazo, I hope I'm pronouncing that correctly, in Ecuador. Because of the bulge of the Earth's equator, that mountain on the equator is further from the Earth's core. So even though Mount Everest is the tallest mountain when measured from the ground, if you're measuring from the Earth's core, thanks to the bulge that the Earth has, the mountain closer to the equator, Mount Chimborazo, is further from the Earth's core than Everest, even though it's shorter when measuring from the ground. I hope that you can see it here. I think the rings of Saturn make it even more obvious. They kind of highlight that it's a little bit wider around the equator than it is from pole to pole. And we can see here a day of just 10 hours and 40 minutes, 10 hours and a half pretty much. That very quick rotation is also causing it to bulge around the side. Even solid rocky objects can do this. If they're rotating quickly enough, spinning in the right way, then solid rocky objects will appear to bulge. Of course, the Earth, we are a solid rocky object today, But that wasn't always the case. The Earth began as a liquid ball of rock. We began as a very, very soft lava material. Now, it looks like we're not getting a good view of Haumea here, but there are dwarf planets, and we can see Haumea there labeled as a dwarf planet. There are dwarf planets who have reached hydrostatic equilibrium. They've become round. They're no longer lumpy and bumpy like a potato or an asteroid, but they are bulging because of their very, very quick rotation. And this also happens to stars. So we're going to hop back a little bit closer to the present day. I just wanted to go back to the very close conjunction that Venus and Jupiter had late last year, just so they were close enough in the sky that we could quickly hop between them, and you could maybe make a little bit of a comparison between their shapes, because they are such different shapes. Jupiter is a lot more oblate than Venus. So here we are, back a little bit closer to the modern day. We'll let the sun go down, and we'll deselect Haumea there. And we're going to come around to Deneb and Altair. So these stars, these blue stars, Altair and Deneb, they are also rotating very, very quickly. So let's see if we can see any difference in their shapes. So we can see that Altair here does look quite round, and if we take a look at Deneb, I'm presuming it will look quite round as well, but just due to the limitations of Stellarium's software. However, stars that rotate quickly, especially stars that rotate very, very quickly, can become almost ellipsoidal in shape or lenticular in shape. So an ellipse is a 2D shape, of course, and an ellipsoid, of course, could be a 3D version of that. But lenticular, the shape of a lens, is sort of an even symmetrical shape. And that's the kind of shape that stars that rotate very, very quickly can be. So we generally think of these things, stars, planets, particularly planets, as being spheres, as being these big balls. But really they are often a little bit off. Venus is very, very close to a sphere, and many stars are quite close to spheres. There are stars that are rotating very, very slowly that would be close to perfect spheres. But the quicker these objects rotate, the more they distort around the equator. So Jupiter and Saturn, for example, rotating very, very quickly, they're quite distorted. They're very much an oblate spheroid, a ball that has been squished a little bit at the top and at the bottom. Even the Earth is an oblate spheroid to a lesser degree, but we rotate much, much faster than Venus. Venus's slower rotation is a big part of why it's closer to actually being spherical. And the same thing does happen with stars. It's unfortunate that we're not able to see it with the level of magnification that Stellarium allows, but stars that rotate very, very quickly, they take on that oblate shape. They take on that shape that is not exactly the shape of a sphere. This is something you might be able to tell over the past few videos when we looked at the eclipses. If we take a closer look at the sun here, it's going to look pretty round. We'll get rid of the atmosphere. It's going to look pretty round, and it is quite spherical because the sun is so large. The little bit of a deviation, the slight widening around the equator compared to the north-south diameter, it's very, very tough to see. And the sun doesn't even rotate quite as quickly as Jupiter and Saturn. It rotates a little bit slower, but of course different speeds of rotation at different locations. This is true for Jupiter and Saturn as well. Jupiter and Saturn, because they're gassy planets, the atmosphere around the equator is moving a little bit faster than the atmosphere at the poles, but the sun is just a gigantic ball of plasma. The gas giants such as Jupiter and Saturn, there is a good chance that they have some sort of core, whether it's a very small rocky core or the more likely core of metallic hydrogen under a lot of pressure. The sun doesn't really have that. It's pretty much a amorphous mass the whole way through. The plasma that's near the center where the actual fusion happens, it is under a lot of pressure, and it may behave closer to a solid due to that pressure, but definitely around the outside the sun is pretty soft. It's amorphous. It's a giant ball of plasma, this phase of matter just above gas, really even looser, a less tight association than the molecules in a gas would have. So the sun also has that oblateness where it's a little bit wider around the middle. So of course I think this is a great thing to bring up when people ask if the world is round. It is round, but it's not a sphere. It's an oblate spheroid, so it is just a little bit off what you might be expecting from the typical globe, but not quite as far off as those gassy planets Jupiter and Saturn. So I hope you enjoyed this video. I hope you enjoyed this little break from the eclipses. We will be getting back to the eclipses, not just for future eclipses in the far future, but for the multiple eclipses we have coming up this year, which we will be reviewing soon. If you did enjoy this video, then please do like it. If you enjoy this kind of content, then please subscribe to this YouTube channel. And if you'd like to read this information, you can do so on my website, queevinscontent.ie. Also, don't forget that I do have other channels, Queevin's Other Content and Queevin's Content Os Gaeilge, which are going to have new videos posted very soon as well. Thank you very much for watching, and hopefully I'll see you back here next time.